Hey everybody, this is Mrs. Ewald, and I'm going to take you through reaction mechanisms. Miss Heaton previously went over rate law, and you should all know how to determine the rate law expression by looking at experimental data and looking at multiple trials. And you went through, you saw for your M and your N and possibly your P, and then also went back and saw for your constant K. I'm going to take you through a different method of figuring out your rate law expression while leaving out your constant K. We'll just leave it as K. You do not have to actually solve for it. So before we get into doing the rate law expression, let's first understand what a reaction mechanism is. Now, I highly recommend that you pay attention and you listen. Only pause and stop when I tell you to go through and do your example. I just feel too many people are fast forwarding way too much, and you never know if I talk about you or say your name, Will. So make sure that you are paying attention. Alright, so reaction mechanisms. Defined as a series of reactions that add up to create a whole reaction. Now we should be familiar with mechanisms because we saw this when we did Hess's law. And in Hess's law, we were able to see how there were multiple steps, step 1, step 2, step 3, and so on, in order to make an overall reaction. Okay? Now, we're going to still be looking at steps. And so we're going to be looking at, well, what are those intermediate reactions that must occur in order for us to get to that overall reaction at the end. So for example here, I'm showing you a mechanism. So here it's showing you step 1 and step 2. I'm also showing you the slow step and the fast step. Now that means something. If we tell you there's a slow step and a fast step, there's definitely something behind that. And so we will see the importance of the slow step in just a moment. A few things to look at when you look at a mechanism is to see first off if there are things that you can cancel out. And if you find anything that appears, so looking down here, appears as a product first and then as a reactant, then you know that it's an intermediate. If you see something appearing first as a reactant and then as a product, it is a catalyst. Now, intermediates, those are never found in your overall reaction. So therefore you want to make sure that they do cancel, and that's how you know your mechanism is correct. Also, catalysts should never appear in your overall reaction because they're not actually part of the reaction. They may be used up or they may not be, but what they do is they help to speed up the reaction. And so catalysts, I should say they may or may not appear in the overall. The rate determining step, as I mentioned, is the slowest step, or the rate determining step. So going back to what I mentioned, the slow step has great significance because that is the step where it's going to be at the most. There is definitely a reason why we say that's the slow step. And so it is from the slow step that we are going to determine our rate law. So you're always going to look to the slow step to determine your rate law. And we'll go through some examples of that. When I say rate law, I'm also referring to the rate law expression, and so that's how we develop this down here. And so we will be able to do many things. We should be able to figure out the rate determining step. We should be able to figure out the intermediate, the catalyst, and then the rate law expression. So looking at this example here, I would be able to cancel out 3B. It's a period as a reactant first and then as a product. So this would be a catalyst. 3B, so B is acting as the catalyst in this reaction to help to lower the activation energy. And then the intermediate, if we have any, so we have 3C, which appears as a product first and then as a reactant. So 3C, so C is an intermediate. Now, notice how the rest of this should now add up to your overall reaction. That is how we could say, yes, this is correct. That is the correct mechanism. And so we would end up with, and this should be 2A plus E yielding D plus F. So this would be the overall reaction for that mechanism. So that gives you the anatomy, all the parts of a reaction mechanism. So let's go through some more examples of how to determine the rate law expression. Okay. So one example that I want to go through, and remember, for any step, the order for each reactant will be its coefficient. So this only applies for equations in a mechanism, and we will kind of cover this when I go through examples of rate law in just a moment. Like, for example, let's go back up here. Sorry if I'm making you nauseous here, but let's go back up here and determine the rate law for this example. I'm going to refer to the slow step, and so I will say rate is equal to K. And then I look to see what are my reactants in the slow step, and it is 2A. So this will then be A2. I'm going to use my coefficient, and you put that as my order. Again, we can only do that for a mechanism, not in the experimental. And then the other reactant, which is E, is not found in the slow step. And so therefore, we would say that E is to the 0 order because it's not affecting the rate of the reaction. And so you could actually leave that off because it's considered negligible. And so then you could just rewrite it as saying rate is equal to K, A to the 2nd order. Okay, now moving on to the example. So with example 1, I'm now showing you a mechanism that has 3 steps to it, 2 fast and 1 slow. Go through and identify any intermediates, and also if there are any catalysts. So in this case, my intermediates, I have N2O2 and N2O. And I don't have any catalyst for this reaction. My overall reaction, I'm now going to see what I have left and take the sum of it. So I have 2NO yielding, and 2 hydrogen yielding N2 and water. So that is my overall reaction for that mechanism. So I'm going to use this to guide me in my rate law. Now, one thing that's new here that we have yet to see is this double arrow. Now, we mentioned a long time ago that this means that it's reversible. And what it's telling you is that this is at equilibrium, meaning that you're forming product at the same rate that you're forming reactant. So it's able to go back and forth, back and forth, back and forth in the fast step. Notice how N2O2 we canceled out here as an intermediate. However, because this is reversible, and if we look to the slow step, in the slow step, you would have N2O2 and hydrogen appear. Now, N2O2 does not appear in your overall reaction, so you would never want that then to be in your rate law expression. However, N2O2 at the same time is also forming back into NO, and we see that because of this this arrow, how it's able to go back and forth, so reversible. And so when we look to the slow step to determine our rate law expression, we would say, boop, 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 rate is equal to K. Now we definitely see H2 in our slow step, and we have 1, so that's coefficient 1, it would be order 1. And NO doesn't appear in the slow step. However, this appears in the slow step, N2O2. And N2O2 in the fast step could also be forming more NO. So we would also want to put in our rate law NO to the 2nd order because of that coefficient. So notice here, because we have that double arrow, it is reversible. We are forming product and reactant, so it's going back and forth. We look to the slow step. We notice that N2O2 is also provided there. It does not appear in our overall. It should not appear in our rate law. However, N2O2 could also be forming back into NO, which is a reactant, which should appear in your rate law. So intermediate products cannot be isolated, so we can't measure their concentrations. So therefore, only species in the overall reaction can be in the rate law, which is what we see here, and you know that it all checks out. So what I would like for you to do now is pause and stop and try this example on your own now. So go through, figure out your intermediate, your catalyst if you have any, write your overall, and then determine your rate law for the reaction. Go. Seriously, stop and pause it and do it now. Go. Okay, so you should be able to get NOCl2 cancel. Then there are no other intermediates or catalysts, so our overall reaction then should appear as 2NO and Cl2 yielding 2NOCl. The rate law for the reaction will be rate is equal to K. Now looking at our slow step, for sure we see NO to the first order. Oops. However, NOCl2 is able to be, because it is reversible, it is able to move back into making NO and Cl. So it's not NO to the first, it is NO to the second order because it appears twice. And then Cl2 to the first. So you have to go back and look at the fast because this is able to go back and forth. Hopefully you caught that. If you did not, make sure you go back, retry it, and you're able to catch the reversible reaction in order to get to the correct rate law expression. Let's go through another example where you don't have that situation, and the first one you see just goes straight through, and we don't see the double arrow, and that is with O3 yielding O2 and oxygen in the slow step, and then oxygen plus ozone yielding 2O2. So the overall, let's see here, if anything cancels, oxygen, so that's an intermediate. Don't have a catalyst, so we end up with 2O3 yielding 3O2. Notice how I'm adding those coefficients up. My overall rate law for the expression then is going to be rate equals K. Look at my slow. For sure, I see ozone. And because I don't have the reversible or any situation like I had before, it's only going to be ozone to the first because that is what appears in my slow step. And you're done. All right, last one. Go through this example on your own and go now. Make sure you're doing it. Okay, you should end up with canceling NO2 and F. Uh-oh, nope. Yep, NO2 and F. Oh, do I have this written right? No. If this is the way, then you would end up with NO2 and F2 yielding NO2F. So then the rate law for the expression would be K, NO2, and F2. Yep, that would be it. All right. Hopefully you are okay with mechanisms as another way of determining rate law. And the next thing we'll do is figure out rate law from graphing. This is Mrs. Ewald signing out. Happy mechanisms!